Thank you for this nice opportunity to present my talk. My talk is more about the ideas and overview of the existing methods for realizations of Lie algebras more than about results. Nevertheless, we started this problem just at the beginning of this year with my PhD student Mykola Starey, and we already knew some interesting answers for some questions. So let me start with the description of motivation of this problem. You can see a rather big list of things how we can apply realizations of Lie algebras, but actually what I want to say is that in real mathematics or in physics, we met continuous symmetries, and these continuous symmetries come to us in form of Lie groups, not in Lie algebras, but Lie algebras is a good instrument to study Lie groups, at least to study them locally, to study them in some not very big neighborhoods, and to study how it's constructed, and at least one component of Lie group. Well, so here you can see a rather big amount of applications. The main three applications, first, second, and the third, I mean construction of invariant models, integration of equations, and group classifications, are the main objectives of our department, some of main objectives of our department, and there are much more other applications. In particular, the realizations of Lie algebras are very important if you would like to apply numerical methods and to construct some good different schemes to approximate derivatives in PDEs when we would like to solve PDEs or systems of PDEs by numerical methods. So that's the motivation. And now let me give you definition of realization of Lie algebra. What we actually do? Actually, we work with abstract Lie algebras. We usually consider field of real or complex numbers and consider a set of some fixed set of Lie brackets. With respect to this field, these Lie brackets or product product of a vector field V should satisfy some standard properties that are required by Lie algebra definition, and we fix a representative. We fix the representative by means of choosing the basis of vector space. In this moment, our Lie algebra is fixed by its structure constant tensor. And so as initial point, we have only structure constant tensor, and we would like to construct the realization. What do we mean by realization? I will use a definition that, as far as I know, first was formulated in our joint work. You can see it below, and I will refer to this work several times during my talk. So, as a realization, we understand a homomorphism of a Lie algebra, abstract Lie algebra, into a vector space of vector fields on some set M. When we are in field of real numbers, it's very convenient to consider this M as some open subset in manifold, in real manifold, but I'm sorry, I should go back. But in the case of complex numbers, it seems that it will be reasonable to consider just domain, just some domain. If each basis element can be represented by a vector field which is non-zero, we will call such a realization is faithful. And that's the main type of realizations which is important for us and which is important for applications. And if the kernel of this homomorphism is not zero, then we will get unfaithful realization. So we obtain realization in form of vector fields, what means that actually we have a kind of differential operators of first order, but these are homogeneous differential operators. This means that we do not consider part of differential operators which correspond just to multiplication of the function. So we work with vector fields only. And these coefficients should be smooth functions in the case of real field, and in the case of complex field, we need these coefficients to be analytic functions, because we need possibility to differentiate them as many times as we need for our concrete problem. Well, that's the definition. So to describe all possible realizations, we need some rule how we will decide if two obtained realizations will be equivalent or not. Now I again will cite you the paper 1, the definition formulated in paper 1, but I would like to mention one detail here. So on our Lie algebra acts a general linear group. It acts on it as on vector field. So it just changed basis of our Lie algebra. And some of the transformations of this general linear group preserve structure constant tensor after our basis elements are fixed. And these elements form our automorphism group for our Lie algebra. And if we take some subgroup of automorphism group, we can consider transformation of one realization, which I called R1, to the second realization R2, by means of two things. The one thing is change of basis, which is provided by automorphism transformations. That means the structure constants are the same. And the second part is non-generate transformations of the coordinates on our manifold. In the case of real numbers, we can treat it as diffeomorphisms of our submanifold. And in the case of complex numbers, we can consider just invertible transformations, non-degenerate invertible transformations. And independence, if we apply or apply not transformations from the automorphisms group, we can differ two types of equivalence. Actually, here is written, and what was really written in our papers, that two realizations are weakly equivalent if we use all the automorphisms group. In fact, when we study weak equivalence now in our work, we suppose that if we use at least one non-identical transformation from the automorphism group, we will say that these two realizations are weakly equivalent. And strongly equivalent if we use the diffeomorphisms or non-degenerate transformations of the coordinates on our domain only. And here you can see very simple and very, very useful example that show us when we start to classify all possible realizations for the field, in present case for the complex numbers, at one stage we get that our third operator under some circumstances can have such a form, where we have this constant C. Of course, if this variable wasn't first fixed, or if we just have two operators, first and third, we can do the change of variables, non-degenerate change of variables over the field of complex numbers, and we will get the equivalent realization which will be strongly equivalent. But in the case of real numbers, I'm sorry, I just clicking, want to show you and switching the screen. I'm sorry. But in the case of real numbers, such a change never can be made, because real field will not allow us to make such a change. And transformation from the automorphism group will be necessary, and such a transformation exists. So if you really want to study all interesting realizations and to avoid such simple differences in our list, we need to use weak equivalence, but not strong equivalence. Well, that was a simple example. Now let me tell you how we can construct realizations. The most transparent and the most complete method is the direct method. This method suppose that we will take M, linear, it not should be M, here should be N, if the N is the dimension of our Lie algebra, because M is a dimension of our manifold or number of variables, but M is a dimension of Lie algebra and number of basis elements. This place should be M instead of M, N instead of M. So we take them in general form and substitute them into our commutation relations, and we get a system of PDEs. We should solve the system of PDEs, should integrate it, and we should consider all possible cases. We can simplify it using the homomorphism of our manifold. That problem is not very simple to solve. Actually, it brings us to a number of branching cases, and it's not so easy to solve it in general case. We managed to do this problem, to do this problem many years ago, something like 20 years ago, with our colleagues, but only for low dimensions. And if you try to apply this method to higher dimensions, if you try to apply this method, for example, for physical interest in Lorentz algebras or something like this, which are 6-dimensional, it's very, very hard to do it by hand. So this method in general, and it's not so easy to apply it. But there are several key things that can help us to simplify this problem. First of all, we always can apply the rectification theorem and to transform one of operators to the shift operator. I mean to the operators that differentiate with respect to one variable only and have the unit coefficient. And we can use the notion of mega-ideal that was proposed by Roman Popovich and which appears to be much more powerful tool than it was at the moment when this paper one was written. And we can construct Lie algebras, structure them one by one, going from the lower dimensions to higher at each step for one dimension more. But the main problem that we should choose correctly the operator that will be transformed to the shift operator. For example, now it seems that we have several arguments that the shift operator should be transformed to one of operators which belongs to the Cartan algebra. In this case, it seems that result will be simpler. The second thing that if we are trying to construct the realizations of physical interest in Lie algebras, all physical interest in Lie algebras have simple subalgebra in their structure. So it's subalgebra, or it can be not subalgebra, but some structure have simple structure, some substructure have simple structure, and so on. And we cannot construct this chain of mega-ideals. And this makes this physical interest in algebras much more complicated for construction of realizations. So what we can do, there are some other methods. One of the methods was, there are some, I forgot to tell you about some helpful things that we can branch in our cases by considering a realization rank, which is formed of matrix of coefficients. This realization rank actually can be changed not by automorphism transformations, neither by diffeomorphism of our space, so non-degenerate transformation. This is an invariant quantity, and it can be used for branching and very helpful. And we can construct realization by means of so-called Shirokov's method. The main idea of this method is to construct left invariant differential one forms, or which are usually called Maurer-Cartan forms, and we can construct them directly from structure constants as a solutions of this is in fact first order partial differential equations, but that's not ordinary PDE. It's first order equation, but with matrix coefficients. But we can solve it in general form and obtain differential one form, matrix of components of differential one forms. Then we can recover left invariant vector field using the duality of differential one forms and left invariant vector fields. This will work in the case if the action of our Lie group connected locally to the Lie algebra is transitive or even more primitive. So it should act on not only transitively, but should have one orbit only. In this case, everything works well, and even more, it works well for transitive actions when we have orbits. But in the case when the action is not transitive, this problem becomes much more complicated. We already solved several cases successfully, but to be honest, we solved these cases due to the fact that we knew the answer before we was applying this method. So we were able to construct the set of subalgebras in a correct way, but the procedure that allows to construct subalgebras of a special that satisfies special conditions is not developed yet. Some attempts were made in master thesis by Daniel Hromada, and now some colleagues from our department continue this work. But this problem is not so obvious. There is also another method, which is very interesting. It was developed by Blattner in 1969. And when he was developing this method, he used the result by Viktor Gulyomin and Shlomo Sternberg from 1964 about the abstract transitive Lie algebra with some subalgebra, which is isomorphic to some differentiation Lie algebra, differentiations of some ring of quotients. And he proposed the following nice formula. This formula also works for transitive cases only. For transitive, the isotropy subalgebra is isotropy subgroup, is allowed. Again, transitive case, but as you can see, his formula essentially involves PBV coefficients, Poincaré-Birkhoff coefficients, which are not described well. There is a good definition of them, but we have, we have no formulas, computational formulas or algorithms, how we can compute them. So one of our hopes is to connect to this approach and probably to get formulas or general description how we can construct PBV coefficients, at least in the transitive case. That's one of our objectives that we are interested in. And the second thing is to try to do it for transitive case. Well, so what we are right now trying to do with Mykola concerning simple Lie algebras. We try to understand how many realizations from the total list of inequivalent realizations we can get from the representation theory. And because for simple Lie algebras, we have well-developed representation theory, finite dimensional representations or so-called weight representations of simple Lie algebras. And we are using the connection between matrix. If we have fixed bases, then the representation has matrix form. It's square matrix of fixed dimension, and using this relation. This relation is standard to physics. Physicists usually use such a relation, but recently I got reference from Yevhen Chapovsky. This construction can be nicely developed from algebraical point of view if you look at the differentiations and general linear transformations of them. So we try to do it. And for example, for the smallest possible simple Lie algebra of type A1 or SL2, now we consider complex case, we will have many realizations. In fact, infinitely many finite dimensional realizations of such a form, as you can see there, and we can study how they correspond to the realizations that can be obtained by the direct method. What is interesting that not all realizations can be obtained from representation theory. Let me show you.
Sorry, Dr. Nesterenko, I am time.
Okay, so
Okay.
I'm finishing. So that's the example which can be obtained. We can attack it by two ways. The first way, we can try a brute force, just try to introduce new variables. For example, replace square by new, by y, then we will see that we need z and so on and so on. And actually we get linear construction, which is infinite dimensional, but it cannot be connected to matrices because not all coefficients are multiplied by variables. Some of them are just constants. That's a problem. So we will think a bit about it. Probably we can propose infinite dimensional representation from that. But another way, if we consider general case and require from this general case possibility to linearize, we get a system of ordinary differential equations. We can adapt some theory into these systems, and we can, using relations between E2 and E3, transform the systems of equations to system of functional equations. And it was very nice because the system of functional equations was linear, and to guarantee the existence of solution, we need a determinant to be zero because it was homogeneous. And this determinant precisely coincides with Jacobian. That means that this will be degenerate transformation. So there is no such a transformation, and this contrary instance to the example that we can get all realizations from the representations. That's all. Thank you. I'm sorry for delay.